Now we know that light is an electromagnetic wave. We're all familiar with the rainbow of colours that make up visible light. But visible light is just one tiny slice from a huge spectrum of electromagnetic waves. You can see the whole spectrum here. They range from the longest wavelength, lowest frequency waves, which are radio waves at the bottom of the diagram, right up to the shortest wavelength, highest frequency waves, which are gamma rays, at the top. These waves all have exactly the same structure of electric and magnetic fields and all travel at the same speed in a vacuum. The only difference between them is in their frequency. Notice that there are no hard and fast divisions between the types of waves, and in fact some textbooks don't include microwaves at all, but just show radio waves merging into infrared waves. I'll just run briefly through the parts of the electromagnetic spectrum. The longest wavelength electromagnetic waves are radio waves. These can have very long wavelengths of even thousands of meters, but the range goes down to about 10 centimeters. We not only use them in radios, but in TV transmissions and other communications. Then, the microwave part of the spectrum has wavelengths from about 0.3 meters down to about 0.1 millimeter. And they're used in mobile phone networks and by our GPS system, as well as in microwave ovens. At wavelengths from about a millimeter down to about 70 microns, we have infrared waves. Note that the waves themselves are not hot because there's no matter there to move, but they are one of the three types of heat transfer because when materials absorb infrared waves, the atoms in the material vibrate more, which means it is heating up. Night vision goggles are made to detect infrared and convert it to a visible image using a colour scale that indicates the temperature of objects. Remote controls use what we call the near infrared, which means close to the visible part of the spectrum, so the shorter wavelength end of the infrared. The near infrared joins on to the red end of the visible spectrum, and that ranges from about 700 nanometers for red light down to about 400 nanometers for violet light. The different wavelengths correspond to the different colours of light. If we see all the colours of the visible spectrum together, we see it as white light, and white light can be separated by a prism or a diffraction grating into the different wavelengths by a process called dispersion that we will see more of later. In fact, we don't need to see all the rainbow for our eyes to interpret it as white. We have cells called cones in our retinas at the back of our eyes that are the cells that detect colour. And there are three different kinds of cones, each with a slightly different combination of chemicals that respond to different wavelengths. So the cones respond to blue, and some to green, and some to orangey red. You can see the graph at the top there, where it's labelled S and M and L, where you can see the peak response of the three different types of cones. So if all three types are stimulated at once, our mind interprets that as white. So that means if we have a light source like a white LED or light-emitting diode, it doesn't emit the whole spectrum, but it has a very sharp peak in the blue and then another lower, broader peak in the green to orange band. And that means all the cones in our eyes detect that at once, and so we interpret that as white. At wavelengths just shorter than violet light, we have the ultraviolet part of the spectrum. We mainly hear of it in ads for sunscreen, but UV is used in various applications like sterilizing medical equipment. UV wavelengths go from 400 nanometers to about 6 angstroms, and an angstrom is 10 to the minus 10 meters. That unit was come up with to describe things of about the size of an atom. The short wavelength end of the ultraviolet spectrum is called the hard UV, and it's in the category that we call ionizing radiation. This means radiation that has enough energy to knock electrons from atoms. So this can break chemical bonds or create new bonds, and so in living tissue this is very damaging and can kill cells. X-rays with even shorter wavelengths are also ionizing radiation, and their effect can be cumulative, which is why medical staff who do many X-rays a day will all go and hide behind screens before turning the X-ray machine on. Gamma rays have the shortest wavelengths and the highest frequencies. They are the most damaging type of electromagnetic radiation. They're caused by reactions in the nuclei of atoms, and nuclear reactions always involve much more energy than the electron transitions of chemical reactions. Gamma rays are used in things like PET, which is positron emission tomography, to make scans of different types of tissue in the body, so they're very useful in medicine. But all of the parts of the electromagnetic spectrum can give us information about the things that gave them out. So, an example from astronomy. These are pictures all of the same nebula called the Crab Nebula, which is a supernova remnant. The electromagnetic waves coming off it at different wavelengths give us a variety of information. At the top left you see the radio waves. They're the result of fast-moving, high-energy electrons spiraling around magnetic field lines. Then the infrared image at the top right shows in green the same accelerating electron radiation, and it also shows hot, bright lines starting to show through that come from filaments of hot gas. The visible light photo at the bottom left shows these filaments more clearly. These gaseous filaments are the result of a cataclysmic explosion that blasted the star's outer shell into space. The X-ray image at the bottom right shows the highest energy particles, and you can see the pulsar that is at the middle of the nebula. There are tilted rings of particles that have been flung outwards from the center, and you can see the two high-energy jets of particles blasting away from the pulsar at right angles to the rings.